Thanks, Ilya, for the introduction, and thanks everyone for coming. So today I want to talk about pseudorandomness in the context of algebraic complexity theory, and tell you about some results that take a bit of a different perspective on the problem than is usually considered in the literature on this. So since this is the first talk on algebraic complexity, we need to go through some of the definitions, make sure we're all on the same page. You know, what are the interesting problems here? What are our base models of computation? So for us, we're going to be interested in algebraic circuits. These are a model of computation for polynomials. These are circuits built out of addition and multiplication gates, just in the same way that Boolean circuits are a model of computation for Boolean functions that are built out of and, or, and not gates. Algebraic circuits compute polynomials, and they're built from basic arithmetic operations. So sort of the way I think about these is the inputs are really formal variables, and the output of the circuit is some formal polynomial. It's really a sum of monomials. Maybe thinking of this as a function is not always the right viewpoint. So for example, this circuit on the slide here, the bottom left gate computes the sum of the variables x and y. The bottom right gate computes the difference x minus y, and then the top gate computes their product, which is x squared minus y squared. And there are two complexity parameters we're going to be interested in: the size and the depth of these circuits. So the size is just going to be the number of wires in the circuit, and the depth will be the length of the longest path from any input to the output of the circuit. So this is our base model of computation, and the algorithmic problem that we'll be interested in is this polynomial identity testing problem. This is a really important central problem in algebraic complexity. I give you as input an algebraic circuit, and I ask you to decide, does this circuit compute the identically zero polynomial? This is somewhat analogous to circuit satisfiability. There I would give you a Boolean circuit and ask you if it computes the zero function. But this problem is different because we actually have efficient randomized algorithms for the problem. You can just take your circuit, evaluate it at a randomly chosen point. If you see zero, probably the polynomial is actually the zero polynomial. If you see non-zero, well, you certainly know the polynomial is not zero. So we have an efficient randomized algorithm for this problem. And this is a really interesting problem to study. It has many applications throughout theoretical computer science. And what I think is really interesting about this problem is it has applications that are to other problems that are not obviously algebraic. So for example, using polynomial identity testing, you could design parallel algorithms for the perfect matching problem. This also has connections to primality testing of integers. And polynomial identity testing is, of course, useful for algebraic problems like polynomial factorization. So it really has a large number of applications. This is a problem we can solve efficiently with randomness. We don't necessarily know deterministic algorithms for this problem. And so there's a question here. Can we design deterministic polynomial time algorithms for polynomial identity testing? And this is really some algebraic version of the P versus BPP problem. It turns out that anytime you have an algorithm which uses randomness, maybe in some algebraic way, I don't really want to define algebraic because I don't have a good definition for it, but oftentimes that algebraic use of randomness is because you're solving this polynomial identity testing problem. So in an empirical sense, this is complete for algebraic RP or algebraic co-RP, whatever you want that to mean. So this is an important problem. We want to design deterministic algorithms for it. How do we normally do that? Well, we try to construct these pseudorandom objects called hitting set generators. So these are sort of a central object in this talk, so I want to make sure we're all on the same page for the definition. So here, we're going to have some set of polynomials, script C, that we're interested in testing. So you should think of these as polynomials with some bounded complexity. And a hitting set generator is going to be a map that takes L variables as input and stretches them to N variables. So you have L variables here and some N polynomials, which are outputs. And we say that this is a hitting set generator for the class script C if for every polynomial f in script C, you have the following condition, that f is 0 exactly when the composition of f with g is 0. So you can think of these hitting set generators as maybe doing one of two things. Either it's kind of a variable reduction procedure where you can take this n-variate instance of polynomial identity testing and reduce it now to some L-variate instance in a correct way. Or if you like to think more about pseudorandomness, you can think of this generator as taking L truly random field elements and stretching them to N pseudorandom field elements. Now, normally there are two parameters of generators that we care about, their seed length and their degree. So the seed length of the generator is this L. It's the number of inputs to the generator. And the degree is just the maximum degree of all the output functions. These are normally the parameters that we care about. Let me give you just a brief sketch of how you use these generators to design deterministic PIT algorithms. So if we have some class script C, some bounded complexity class of polynomials that we're interested in testing, and we have a generator, well, there's sort of two obvious PIT algorithms we can run. One is just the trivial brute force algorithm, where you take your polynomial, you evaluate it at many different points, enough points to correctly conclude whether or not this polynomial is 0. And the number of evaluations you need here is exponential. It's something like the degree of the polynomial raised to the number of variables. Now, on the other hand, if you have a hitting set generator for this class, you can design a different algorithm, which is you first take your polynomial, compose it with the generator, and then test that composition by brute force. And what is the running time of this algorithm? Well, it's the same shape. It's going to be degree raised to the number of variables. But now here, the degree is really the degree of the composition. So you get the product of the degrees. And the number of variables is this L, the seed length of the generator. So if you can design one of these generators where you can efficiently compute it, the degree is not too large, and the seed length L is small compared to N, then you're going to get a faster deterministic algorithm. That's usually the goal here. Usually, we want to minimize the seed length of the generator. That's our primary concern. And then we want to keep all the other parameters reasonable enough. We can tolerate polynomial degree. We can tolerate polynomial time computability, maybe even super polynomial computability, depending on what the seed length is. And in this talk, I want to do something different. I want to focus on the complexity of the generator itself. So that I want to take as the first class concern. We're going to minimize the complexity of the generator as much as we can, and just try to keep the other parameters of the generator, say, non-trivial. Of course, we'd like to get the other parameters as efficient as possible, but really I want to take the complexity of the generator to be our first class concern. And why would you do this? Well, there's a few reasons. I just think this is a really natural, nice question that hasn't been studied much in arithmetic complexity. There are not really many works that explicitly look at this problem, and I think it's nice. So, it's 2025, everything's an ad. This talk is an ad. Really, I want to just convince you all that this is a nice problem and hope that some of you will work on it. Of course, I had to buy the ad, so I had to pay a theorem. So I'll show you the theorem that I paid for this ad slot. But beyond just, it's a nice question, similar questions have been studied in Boolean pseudorandomness and in cryptography, where we have NC0 constructions of one-way functions in PRGs. And those turn out to be really interesting constructions that have applications within complexity and cryptography. So maybe there are similar nice applications of these objects here in arithmetic complexity. There's some connection to algebraic proof complexity and some open problems there that I'll mention in the next slide. And finally, I want to say there's some superficial connection to this theory of algebraic natural proofs, where we're interested in understanding, can we actually prove algebraic circuit lower bounds? Can we prove VP different from VNP? We don't really know if our techniques work there. We have a notion of a natural proof. We don't know if there's a natural proofs barrier. And to show that there's a natural proofs barrier, you need to construct a pseudorandom object which is superficially similar to these low complexity generators. There you need more like a succinct generator, which is still asking for some fact that the generator has much lower complexity than the things it hits, but it's a slightly orthogonal direction on the question. But all that's to say that, aside from this question being sort of a natural, interesting one, it has connections to other parts of arithmetic complexity. And I want to highlight a little bit the connection to algebraic proof complexity as a bit of a motivating question for this work, and also to give you some idea of why the construction and the theorem I'll tell you about is interesting. So we saw some proof complexity yesterday. So this is more about the algebraic side of proof complexity and algebraic proof systems. So our setup is, we have a system of polynomial equations, which is unsatisfiable. There's no solution. And what we're interested in is how easy or difficult is it to prove the unsatisfiability of this system. And for me, the proof system that I'm interested in is this ideal proof system introduced by Grochow and Patasi some years ago, where, what is our certificate of unsatisfiability? It's going to be this Null-Stellensatz certificate, where you write some combination of the FIs, you find some GI polynomials, so that the sum of GI times FI is identically 1. And if you find this certificate, this means there is no solution, because otherwise a solution would imply 0 equals 1, which is contradiction. And over algebraically closed fields, these refutations always exist. And you can measure the complexity of your refutation by considering something like the algebraic circuit size of these GI polynomials. Right, so this is a well-studied proof system. There have been a number of lower bounds that have been proved for this over the past, say, 5, maybe 7, 8 years. But one thing that I want to point out is that naturally, proof complexity is sort of this program towards proving that NP and co-NP are different. And if you want to do that, say with the ideal proof system, you need to prove lower bounds for systems of polynomial equations that encode an instance of the 3-SAT problem. Right? You need your polynomials to encode a 3CNF formula. And let me tell you, what do those polynomials look like? Well, for example, if you take a clause, which is, say, x or y or not z, well, you encode it by this very simple polynomial, x minus 1 times y minus 1 times z equals 0. This forces either x has to be 1, or y is 1, or z is 0. And of course, you write down some equations that force all the variables to be Boolean valued. The key point here is that these polynomials that encode the clauses of a 3CNF formula, they're polynomials of constant size. And current techniques in proving lower bounds for IPS, they can't prove lower bounds for systems of equations that encode 3CNFs. You need some complexity in your system of equations. I don't want to get too much into this, but if you're interested, I can be more than happy to tell you during the break. But let me just say that designing low complexity hitting set generators in polynomial identity testing land, these are sort of a necessary step towards proving lower bounds for simple systems of equations like those that encode 3CNF formulas. So this is some motivation that this pseudorandomness problem is related to proving lower bounds in proof complexity. Okay, so enough motivation out of the way. Let me tell you about some theorems. So in this talk, I'm only going to discuss hitting set generators for low depth arithmetic circuits. So we're only going to consider circuits of some depth delta, where delta is your favorite constant, -3, and you can think of circuits of polynomial size. The reason for using low depth circuits as the model case, I can prove things unconditionally here. The paper has some conditional constructions as well, but this just lets me say theorem statements which are true. We don't need to talk about assumptions. So I'll tell you about 3 different generator constructions, and we can kind of compare the different parameters they get. So the first construction of hitting set generators for this class of circuits is due to this wonderful work by Lemaya, Srinivasan, and Tavanas, where they proved super polynomial lower bounds for low depth arithmetic circuits. And as a corollary, using some hardness randomness work, they were able to design hitting set generators. Now their generator has seed length n to the epsilon for your favorite constant epsilon. It has degree log n over log log n, so fairly low degree. But what I want to point out is the complexity of this generator. If you want to hit circuits of depth delta and polynomial size, you're paying about the same complexity in the generator itself. The generator will be computable by circuits of polynomial size and depth delta, but you can't really do too much better than that. For experts in the room, it's sort of a reconstructive generator, so you're not going to get complexity too much lower than the circuits you're hitting. So this is a really nice work. There's a second generator for this class, which came in some follow-up work by myself and Michael Forbes. It has the same seed length, but the degree and the circuit complexity of this generator are improved. And what I want to point out here is the complexity of the generator is much smaller. You get circuits, you can compute this generator with circuits of near linear size, and depth, which is only dependent on this epsilon here in your seed length. It's depth something like log 1 over epsilon. So now you have a generator that can be computed by circuits of, say, depth 10, but manages to hit circuits of depth 1,000,000. Right? There's some imbalance now between the complexity of what you're using to compute your pseudorandom object and what it can hit. There's also a construction which is implicit in some work of Niraj Kayal from 2009, where he constructs generators in a very different regime of parameters. So Niraj's work, it gives you generators where the seed length is much, much worse. You get something like seed length n minus n to the 1 minus epsilon. So there's some sublinear additive stretch for this generator. But the other parameters are really excellent. You have every output of the generator is a degree 2 polynomial, and it's actually computable by a formula of size 3, constant size. So here you're getting an extremely simple generator. The seed length is not so great, but everything else about it is really wonderful. And the main result of this work, and the thing that I want to tell you about, is really a different construction and a different proof of a generator with the same parameters. So you might ask, well, why is this a theorem? It's the same parameters. It's a bit of a technical point that I won't get into much in this talk, but the techniques underlying this proof are more applicable in this proof complexity setting. Somehow the proof of correctness of this generator has more to do with circuit complexity, whereas Kayal's argument is more mathematical. It's maybe more information theoretic if you stretch the analogy a little bit. Okay, so this is the sort of the main result that I want to tell you about, is this different construction of a generator. Yes, really? Both of these are for any, you have some fixed generator here that hits any polynomial. I would have to think more about that. I think there's a way maybe if you pay a little bit more in the depth, you'll get any polynomial there. Yeah. Any other questions? Okay, so I want to tell you about this new construction here. And in particular, I want to give you an idea of how do you prove the correctness of this? I think there's something interesting here that's unique to polynomial identity testing that I don't know an analog of in Boolean pseudorandomness. So I want to tell you about this because I think it's interesting. Okay, so say we have some candidate hitting set generator that we want to understand or analyze. It turns out that there's a certain object that is really useful in the study of hitting set generators. This is what's called the annihilator ideal of the generator. So I want to take my candidate generator G and look at the set of all polynomials f so that f composed with the generator is identically 0. These are all the functions that my generator fails to hit. Now, if you just tease out all the definitions, right? This is just parsing definitions, nothing crazy going on here. Say you have a class C of bounded complexity polynomials that you want to hit. Well, the fact that your generator hits script C is equivalent to the following statement, that if you take the annihilator ideal of your generator and you intersect it with your bounded complexity class, you should only see the 0 polynomial, right? That's the only bounded complexity polynomial that breaks your generator. And so really, this is saying that if you want to prove correctness of some candidate construction, this is entirely equivalent to taking every polynomial in the annihilator ideal and simultaneously proving circuit lower bounds for all of them. Now, of course, this is true. Most proofs of correctness of a generator don't actually do this. They say that, well, I'm instead going to look at polynomials from my weak circuit class and show that those are too weak to distinguish the generator from something truly random. Here, we're going to actually use this as a method of proof. We're going to take a candidate generator, look at everything that breaks the generator, and say, well, those are large complexity. So the generator must hit everything of small complexity. Why does it hit things of small complexity? Well, I can't tell you why those are weak, but I can tell you why breaking the generator is hard. Okay, so let me give you a warm-up to explain how you might use this perspective. So say we want to hit depth 3 circuits with a generator of non-trivial seed length, just n-1. We want to save 1 bit. So one idea you might consider is, well, let's take a generator that has n-1 inputs, and let's just append some hard function to this string of inputs. And in particular, maybe we pick a hard function that, a function that's hard for depth 3 circuits. Right? This is a natural thing you would try. And if you look at this generator, you can understand exactly when it works and when it fails. It's a fact you can prove using some basic algebra that if a function, if some polynomial vanishes on this generator, right? So I have a polynomial that takes the n-1 variables as input, and then if you plug in f, it vanishes. Well, this happens exactly when y minus f is a factor of this polynomial h. So really, this is saying that we need to choose a polynomial f, not just so that f itself is hard, but so that multiples of y minus f are also hard for low depth circuits. So let's revise our idea here. We're going to pick some function f so that multiples of y minus f are hard. And then we can just do this off the shelf using known circuit lower bounds. Say, for example, we can take the determinant, and we know that y minus the determinant will be hard for depth 3 circuits. Okay, so now we have a generator that hits depth 3 circuits. It has non-trivial seed length, but it has extremely high complexity. So how are we going to improve on the complexity of this generator? And the idea is we're going to use a system of polynomials that encode a computation of the generator. So let me give you an example here. These are, in the paper, what are called local encodings of circuits. I'm going to define these by example. Okay, so I don't have enough board space to, I don't have enough board space to draw a circuit for the determinant. But say, this polynomial x1 squared minus x2 squared, say this was actually our hard polynomial. We're going to write down a generator that encodes this circuit. So this generator will have 5 inputs. 2 of them correspond to the inputs of the circuit. And the other 3 correspond to the 3 gates of the circuit. Now, what are we going to do? Well, we need stretch 1, so we need 6 outputs. The first 2 outputs of the generator will just repeat the inputs of the circuit. The next 3 outputs of the generator will be polynomials that are intended to encode the computation. So if you think of y1 as being equal to as y1 capturing the value at this gate, it should be equal to the sum of x1 and x2. Right? So we write down a polynomial which, if you imagine an implicit equals 0 here, this is really an equation saying that y1 computes correctly. You do the same thing for the other 2 gates. And then you would finally we need some extra output. We might as well include the variable that corresponds to the output gate. So this is the kind of construction that we use to make everything very low complexity. And it's sort of clear that if you're using one of these local encodings of a circuit, well, you're going to get some non-trivial seed length here. You'll get 1 bit of stretch in your generator. All the polynomials we saw on the previous slide, they're degree 2. So they're very simple. In fact, every output can also be computed by a formula of size 3. So all of these polynomials, they're very simple. You're getting some non-trivial stretch. But the question is this thing actually pseudorandom? What does it hit? So can we understand the annihilators of generators that look like this? And it turns out you can. And that's sort of the main technical contribution of this work, is a complete understanding of what are the polynomials that break these generators. It's not too hard to show that if you have a generator that's a local encoding of some circuit that computes a polynomial f, then everything in the annihilator is a multiple of 1 polynomial. And what is that polynomial? Well, you have some variable, say zn plus s plus 1. This is the variable that would correspond to that output of the circuit, minus the polynomial f on the first n variables. So this looks like this y minus determinant we saw earlier. It's similar to that, but now there's some extra error term g here. But the point is this g has some structure. Every monomial of g is divisible by some variable that corresponds to an intermediate gate of the circuit. And you could think about, well, if you set all of these variables to 0, then you would project this whole polynomial just to z minus f, which that feels like we're back in this situation where we just need z minus f to be a hard polynomial. So this is actually quite a lot of structure that we can work with. And now I can just give you a proof sketch of how something like the local encoding of a circuit for the determinant would actually hit low depth circuits. So here's the proof sketch. So first off, we know that if we take this very low complexity generator, we understand exactly what the annihilators are. We know what functions we have to fight against. They're just multiples of z minus determinant plus some controlled error term. And now using some sort of basic arguments in arithmetic circuit complexity, you can show that if you had a small low depth circuit for some annihilator, some multiple of this guy, you can get a small low depth circuit for some multiple of the determinant. This is a fairly standard argument in arithmetic circuit complexity, but I don't have time to go into the details. And now you just conclude by saying, well, actually, every multiple of the determinant we know requires large low depth circuits to compute. So in fact, it must be the case that no annihilator of this generator had a small low depth circuit. So that's how you prove these are pseudorandom. So that's all I really wanted to say about the proof and the techniques. Let me just wrap up with some questions that are left open by this work and again, go back into advertising mode. One question is that all the generators constructed in this work, they start with a hard polynomial that has small circuits. So in particular, you can't find low complexity generators that actually hit large algebraic circuits. So I think that would be a really interesting question, to find some construction here that can hit circuits. Second question is, can we understand the parameters of these kinds of low complexity generators better? This is getting very, very small stretch. It's getting sublinear additive stretch. Can we actually get a generator of linear stretch? Are there barriers to improved parameters for these? I don't really understand this parameter space, and I think there are interesting questions here to better understand it. And finally, there's a connection to lower bounds for 3 CNFs in the ideal proof system, or fragments of that. Could we actually make some substantial progress on this and prove CNF lower bounds in restricted subsystems of the IPS. So that's all I wanted to say. Thanks so much for your time.